Good day, everyone. Thank you for joining me today. It's a pleasure to present our research titled Leveraging Machine Learning for Predictive Sustainability Analytics, Optimizing Resource Management in Manufacturing at the 2025 International Conference on Advanced Machine Learning Intelligence and Cybersecurity Technologies in ICT 2025. This research is a collaborative effort by me, Mashuk Rahman Utsho, Arif Ahmed Sizan, Arifa Ahmed, Baizid Kamal, and our colleagues. And it focuses on how advanced predictive modeling can fundamentally change the way industry approach sustainability. The urgency for sustainable solution is clear. Buildings currently account for nearly 40% of global energy use is a significant share for greenhouse gas emissions. With our rapid industrialization and population growth, this energy demand is only increasing. The manufacturing sectors is therefore a critical area for energy optimizations and sustainability improvements. The challenges is that traditional forecasting methods such as simple time series analysis often fail to capture the complex, non-linear energy pattern generated by modern infrastructures. This complexity is exactly where machine learning can provide a powerful and high resolution solutions. Prior research has already established the potential of machine learning in various sustainability domains. We have seen machine learning used in waste management to predict generation and compositions based on socioeconomic factors, and in the circular economy to optimize resources flow and supply chains. Predictive analytics also help with inventory optimization, reducing material waste by accurately forecasting stocking needs. While comparative machine learning analysis is common for general energy modeling in different building types. Our research provides a specific deep dive into energy consumption and resource optimization, specifically within the highly complex manufacturing sectors. The primary objective of our study was to develop and rigorously test a machine learning based framework capable of accurately modeling and predicting energy consumption within a stimulated smart manufacturing environment. Our key contributions center around 3 points. First, we provide a comparison of multiple core regression model, linear regression, elastic net, and random forecast. Second, we implement a stacked ensemble model to strategically combine the strength of these base learners and boost predictive generalization. Finally, we will offer a reproducible machine learning pipeline that can readily adopted for sustainability analytics in other industrial settings. Our overall solution relies heavily on predictive analytics to deliver actionable insights. In the methodology part, we will show you the approach to modeling energy consumption. The data for these studies come from a Kaggle dataset design to replicate our smart manufacturing plans. It contains 1000 instances, with our global being to predict the target variable energy consumption measured in watt per hours. The key predictive features we utilize are ambient factors like temperature and relative humidity, operational factors like occupancy and lighting level, and infrastructures factor like HVAC usage. We also incorporate temporal elements such as the day of the week and whether it is a holiday. We followed a systematic process to ensure a robust and reproducible model. Our workflow begins with data collection, acquiring the raw sensor of data, This was followed by comprehensive data processing, where we cleaned, encoded, and scaled the features. Next, we performed model training, applying and our suite of machine learning regression algorithms. Our analysis phase focused on evaluating feature importance to understand the true divine of energy use. And finally, the evaluation compared the model performance using standard metrics like mean absolute error, root mean squared error, and the coefficient of determination. A brief look at the data shows that energy consumption distribution is near normal, but with a slight right skew indicating occasional high energy peaks. More importantly, our feature correlation matrix revealed that temperature has strongest positive correlation with our energy use, with an R value of 0.70. Secondary factors like HVAC uses are equal to 0.29 and occupancy, which is R equal to 0.19, are more significant. The initial findings confirms that our model would need to account for a mixture of strong linear diverse and more complex nonlinear operational factors. To handle this mix of relations, we selected three distinct Bayes regression models. Linear regression served as our baseline to compute the fundamental linear trend. We then used ElasticNet, our regularized linear model, because it is excellent at handling potential multicollinearity and simultaneously performed feature selection. Thereby, simplifying the model, finally we included random forest, a powerful tree-based ensemble approach, specifically to capture any complex nonlinear integrations such as how HVAC use might drastically change during a holiday period. To further refine performance, we implemented a stack ensemble models. This is a multi-level approach that combines the strength of this Bayes model. Our Bayes learners, linear regression, ElasticNet, and random forest generated their initial predictions. We then trained a meta learner, specifically a ridge regression model, on those predictions. The overall goal of stacking methods is to balance the reliable linear prediction from ElasticNet with a nonlinear flexibility of random forest, ultimately creating a more robust and generalized final model. Now for the results. We compare the performance of all models on the test set, aiming for lower MAE and RMSE and higher R square. We found that ElasticNet model demonstrated the best all-around performance, achieving an R square of nearly 0.60. Linear regression followed immediately behind it. Surprisingly, the complex random forest model and even the stack ensemble performed slightly worse than the single, well-regularized Rayleigh model in the specific prediction tasks. This suggests that manufacturing data, the underlying patterns driving energy consumption, were predominantly linear. Looking at the prediction plots, the quantitative results are visually confirmed. The prediction for ElasticNet, linear regression, and the stack ensemble tracks the actual energy consumption value very closely and indicating high accuracy. In contrast, the random forest model is shown to be more volatile and struggle to capture the high peaks and low valleys as effectively as the linear models did. This reinforced our findings that regularization was more important than nonlinearity for predicting this dataset energy use. The feature importance analysis provided the most actionable insights. Across all models, temperature is overwhelmingly the most important predictor, contributing around 90% of the predictive power. HVAC uses, which is 60%, and occupancy uses, which is 40%, are also consistently ranked as highly influential. These results directly guide resources management, telling the smart manufacturing plants where to focus its optimization efforts, namely minimizing temperature fluctuations and controlling the HVAC system relative to human occupancy. In conclusion, our study confirms that machine learning, particularly regularized linear model elastic net, is highly effective or predictive sustainability analytics in manufacturing. This model provides accurate data-driven energy forecasts, which is crucial for enabling smarter and more sustainable resource management. However, we acknowledge two key limitations. The dataset was static and relevantly limited in size, and our model did not fully leverage long-term temporal relationships. Therefore, future work should explore advanced temporal forecasting models such as deep learning or LSTMs to better capture time series dynamics. The ultimate goal is to integrate these predictive models directly with our real time adaptive control system in smart factories. The research is built for the foundational laid by several excellent students in energy modeling, circular economy, and machine learning, which are listed over here. Thank you all for your time and attention. I hope this presentation has given you a clear view of how machine learning can have leveraged to drive real world sustainability results. I am now happy to take any questions if you may have.